Hello everyone, welcome back. So far we have learned a lot logically about linked list data structure. We saw how to logically represent a linked list data structure in memory, and we learned that a linked list data structure is made up of different nodes, and each node connected to each other via pointers. Basically a node having two parts, a data part and a link part. So in this video and subsequent video, whatever properties we talked about a linked list data structure, we are going to implement our own linked list data structure. We will first implement single linked list data structure, and the operations we learn what operations we can perform on a linked list data structure and the cost of each operations. Then we will be implementing doubly linked list, circular linked list, and all the operations we can perform. To recap, let's talk about some of the properties of linked list data structure. We saw that a linked list data structure has dynamic size. It can grow or shrink dynamically as the element are added or removed. Then sequential access. Elements in a linked list are accessed sequentially from head to tail. We cannot access elements randomly like array data structure because items are not stored in contiguous blocks of memory, and using the head pointer or the address of the first element, we cannot calculate the address of the subsequent list nodes in the list. We also spoke about node structure. A linked list consists of nodes, as I said, where each node contains data and a reference or a pointer to the next node. Think of a node just like a container of data. We can put this container, we can put anything in this container we want. Beside this data, we store a pointer also. Think of it as a bucket of data. We can either use class or struct to put together a group of data. Then we spoke about memory efficiency of linked list data structure. Basically, it can be memory efficient compared to other data structures because they allocate memory dynamically as needed, and they deallocate the memory not needed dynamically. Then we talked about insertion and deletion operation on linked list. Basically, inserting or deleting an element at the beginning or end of linked list can be done efficiently by adjusting the pointers. So if we have a pointer at the head of the linked list, and also if we have a pointer to the tail or end of linked list, so we can add at the beginning and the end of linked list by constant time or big O of 1. So we will see all these operations and properties of linked list practically, and we will implement our own linked list. Then we spoke about random access. Linked lists do not support direct or random access to elements like array data structure. To access a specific element, we need to traverse the list from the beginning or use a doubly linked list to traverse the linked list backward. Then we spoke about the flexibility of a linked list. Basically, it provides flexibility in terms of insertion and deletion and reordering of the element, as it requires only adjusting few pointers. Then dynamic operations, adding or removing or modifying elements in a linked list can be done in constant time complexity or big O of 1, depending on the operation and the position of the list we want to perform the operations. So we will see all these properties, and we will implement them in our own linked list. Then we spoke about overhead. Linked lists basically have some overhead due to the extra memory needed to store the pointer or a reference to the next node. Then we also spoke about iteration. Traversing a linked list involves iterating through each node, which can be done using a loop, a while loop, or it also can be done recursively using recursion. So this property makes linked list a useful data structure in scenarios where frequent insertion and deletions are required and random access is not the primary concern. So say I want to represent a list having number 3 pointing to number 8, pointing to number 15, pointing to number 30, and the node containing number 30 or item 30 pointing to null indicates the end of the list, meaning that after this node we will not have any any other subsequent nodes. So basically we will visualize and implement our own linked list for programming languages that does not have a built-in linked list data structure. So let's see how we can represent a node. I'm going to use C# in this lesson, but once you learn the concept is going to be the same. You can use any programming language to implement your own linked list data structure. So let's jump in and see how we can represent a node. So I'm going to use a class to represent a node. As I said, a node can have a data part and a link part. So in this video, we are going to implement a singly linked list. So I'm going to remove this previous pointer, so we don't need it. So I'm going to make this class field or property a private property, private end data. As I said, we can think of this node as a backend of data. We can put as many data as we want. We can put complex data. We can put another linked list here. We can put user-defined data, string type, any type of data. But for the simplicity of this video, let's only store integer data in our node. Then a node has a link to other node. Basically, this is a reference or a variable of type node. This will be used to store the memory address of an object of type node. So I'm gonna also make this private. To make these private fields accessible and encapsulate them, I can either create getters and setters for these private members, or I can use the C# property. So C# properties provides a way to encapsulate fields or variable within the class and express them through consistent interfaces. So I'm gonna create two properties. Basically, properties are like getter and setters in other programming languages. Or as I said, if you don't want to use property, you can define a getter and setter, public getter and setters for these two fields. So I'm going to use properties. So property, the first type is going to be int, and I'm gonna the convention is, so the name of property should be same as the name of the field, and we are going to give a capital letter. The first letter of the property should be capital. So data, this property is going to have two main components, a getter and a setter. The getter basically retrieves the value of the property, and the setter assigns a new value to the property. So using this getter component, I can return the field I want. So in this case, I just want to return the data, or I can use this dot return this dot data. Okay. And using the set component of the property, I can set the new values the user pass. So I can say this dot data equal to value. I can do the same for the node property. So prop, this time the data type of the property is going to be node, and I'm gonna call it next. So in using the get component, I can return the next property or the field of this class. So inside the get, so I just say return this dot next, and in the set component, I'm gonna set this dot next equal to value. So this way we can encapsulate these two fields of the node class. I'm gonna also define a constructor for this class. So whenever the user make an object or make a node, he should pass a data of type integer. So I'm gonna receive int data. So what I'm gonna do is every time the user passes, it creates a node, he should pass a data, and I say this dot data equal to data. As in the previous video, when we as I said, when we create a node, initially the node will have a data, and the pointer of the node is going to point to null initially. So say I want to insert 3, and the pointer of the node is going to point to null. So I'm gonna initially set the pointer to null after I inserted the data. So I'm going to say this dot next equal to null. So this way we can create a node, or even if you want to make it more simpler, instead of using the fields and the properties for the fields, we can use directly properties to indicate the data part and the link part of the node. So I'm gonna make it more simpler by defining prop, let's call it int data, sorry, properties, int and data is going to have get and set component. Then I'm gonna have prop a node, let's call it next, and this is also going to store the data. So this is going to store the pointer to the next node, so it's going to store the data in the node, and this is going to store the pointer to the next node. So we are going to make our node definition simpler. So I'm going to delete all these. Instead of having the field data, I'm going to use the property with capital letters. So this is our node definition. So as I said, when we implement our linked list, we always keep a pointer to the head node or the first node of the linked list. So to implement my linked list, what I'm going to do, I'm going to create a class to hold all the properties of my linked list and the functions I can perform on the linked list. So I'm going to create a new class by right-clicking on the project name and go to class. So let's call our class my link list. So it's going to be a singly linked list. So inside the class, as I said, we always keep a pointer to represent our list. So this pointer is going to point to the first element of the linked list, usually called as head pointer or the first pointer. Using this head pointer holding the address of the first element, we can traverse the linked list and access all the subsequent elements in the linked list. So what I'm going to do first, I will hold the pointer for my linked list. So I'm going to create a head pointer. So let's call it head. Initially, when I create my linked list, this head is going to point to null, meaning that there is no data element or there is no node in my linked list. So when head points to the null, it indicates that the linked list is empty. So what I'm going to do is I'm going to create a private, let's call it head, and the type of the head is going to be node head. Because it's going to store the address of an object of type node. So in the constructor of my linked list, I'm going to set this head pointer to null, because whenever a user creates an object of this my linked list, the linked list should be empty. Public my class, and inside this constructor, I'm going to just set it to null. And this dot head equal to null. So if I go to program.c, so let's get rid of these lines of code. So if I make my linked list, let's call it list equal to new linked list, new my linked list. So this list is currently empty list because the head pointer is pointing to null. To insert a node in this linked list, what I'm gonna do is let's close this one also. Let's define a function to insert a node in this linked list. As I said, when we want to insert a node, the first thing we are going to do is we will create a node. Say I want to insert number 3, so I create a node. This node may have an address, say 600. So I insert number 3, and the pointer of this node is going to point to null initially. So let's do that. Let's first create a node. So I'm gonna create a function to do this for me. Let's call it public void. Let's call it insert at end. Let's first implement inserting an item at the end of the linked list. So this function is going to take an integer value. Let's call it data. So first of all, what we are going to do, we are going to create a new node. So I'm gonna create a node, let's call it new node equal to new node, and we pass the data. So this new keyword is going to create an object of type node, and it will return the address of this object, and the address of this object is going to be stored in this reference variable new node. So if we go to definition of this, it's going to assign the data we pass to the data property and the next to the null. So the next we will check if our if our linked list is empty, by checking if head is pointing to null means the linked list is empty. So this newly created node is going to be our first node or first element in the linked list. So what I'm going to do is I will have the head pointer, instead of pointing to null, I will have the head pointer to point to this newly created node. So head pointer is going to store address 600. So let's do that. First I'm going to check if this dot head equal to null. If the linked list is empty, so what I'm gonna do is I will just set this dot head equal to new node. So we have only one node in our linked list. Else, if we have more nodes, what we are going to do, we will do something else. We will insert at the end of the linked list. So let's say I want to insert number 8. So what I'm gonna do is first I will call the insert at end function. The insert at end function first will create a node. Let's call it this node may have address 100. Say I want to store number 8, and initially this is going to point to null. So when I call the insert at end function, what is going to do, if it will first check if the head is null. In this case, head is not null because head is pointing to address 600. Then we go to the else block. In the else block, we are going to start from the head. We'll traverse the linked list starting from the head, going all the way until we find the end of the list. So how we know end of the list? Any node whose next pointer is pointing to null indicates the end of the list. So we take a pointer to the first element of the node. We check if it is next is null. No, it is next is not null. It's storing 100. We increment the pointer and going to the next element or the second element. We again check if it is if this node's next pointer points to the null. No, it doesn't. We jump to the third element and increment the pointer each time using a while loop. Then again we check if this node's next is pointing to null. No, it doesn't. We jump here. Once we find a node whose next pointer is pointing to null, yes, this does. So we have a pointer to the end of the linked list here. We can easily insert a node here. So by just having this null pointer pointing to the newly created node, say I want to insert a node here having address 500. So what I can do is, once I got a pointer here, I can, using that pointer, I can easily change this next pointer pointing to address 500. So this will point here and this will have null. So right now this is the end of the list and this is not the end of the list. So this way we can add an item to the end of the list. So first of all, let's define a pointer or a temporary pointer pointing to the head, and each time we increment the pointer until we reach the end of the list. So we are not going to use the head pointer because we don't want to move the head pointer every time, because if we move the head pointer, it's going to disrupt the other operations we might have later on. So for that, I'm going to define a temporary pointer. If I come at the else block, so what I'm going to do is I will define node, let's call it temp, and I will set it to head pointer, because I'm gonna start traversing from the beginning of the list. So initially the temp pointer is pointing here. So let's say this is the temp pointer. So each time I increment the temp pointer and move the temp pointer here, then move the temp pointer here, move the temp pointer here, until I reach the end of the list. So let's do that using a while loop. We can check if the temp pointers next is not null while temp, let's give it a p also, temp, while temp dot next is not null, we are going to just increment the temp equal to temp dot next. This way we can jump to the next node. We set the temp variable to its next node. So once the next node is null, the temp variable is pointing to the last node. So here we can insert the newly created node. So this newly created node, we can insert it at the end of the linked list by just saying current or temp dot next equal to new node. So this way we can insert an item at the end of the linked list. Let's write another function to print our linked list so that we can see whether we have successfully inserted an element at the end of the linked list or no. To create a print function, what we are going to do, we start traversing from the beginning of the linked list. We set a pointer, say a temp pointer, initially pointing at the head, and we will check until the temp pointer is not equal to null. We just keep updating the temp pointer, so we move temp pointer from this node, then the second round of loop we move temp pointer here, and we move temp pointer here. Once the temp pointer is equal to null, we stop looping, and each time we loop, we print the data part of each node. So let's do that by defining a function. I'm gonna call this function public void, let's call it print. So first of all, I'm gonna define a temp pointer of type node temp equal to this dot head. So this temp pointer is also pointing to the head node. First, I'm checking if this dot head equal to null. If the list is empty, I just wanna prompt the user the list is empty, and I return, so I'm not gonna do anything. Else, what I'm gonna do is, using a while loop, I check while temp is not null. While temp is not null, I'm just gonna increment the temp. So temp equal to temp dot next. So, but before incrementing the temp, I'm just gonna print the data portion of each node. So using the temp dot data, I can print it temp dot data, and okay, this is not temp dot data. Then between each data, I'm gonna provide a white space or an arrow like this. So this way we can print our elements in the linked list. So let's check our program. So I have created an empty list, so let's call list dot print. So I'm gonna print an empty list. It says the list is empty, so let's insert few items. So I'm gonna insert 3, 8, 15, 30. So let's first insert list dot insert at end. I'm gonna insert 3. I have only one element in my linked list, so let's insert another element. Let's insert 8, 15. Okay, each time it's printing a new line, so I'm gonna change this to write only, so we don't want a new line. As we can see, the insert at end function works. So let me insert another item. I want to add 30. Now let's take a look at the time complexity of insert at end function. So when we call this function, this statement is going to take constant time, or big O of 1. This is going to take constant time, constant time, constant time, constant time. But where we reach the while loop is going to execute n times, where n is the size of the linked list. So we start looping from the beginning of the linked list and go all the way up to the end of the linked list until we find the end, and we insert at the end. So we start here, move the temp pointer here, 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 until we find the end node, and we insert at the end. So this is going to take big O of n, or linear time complexity, where n is the size of the linked list. So because for each insertion we start from here and go all the way to the end of the linked list. To make this insert function having constant time or big O of 1, or as I said in the previous video, what we can do is each time we insert an item, we are going to keep a head pointer pointing to the first element. We're gonna keep the head pointer, and at the same time we keep another pointer called tail pointer. Let's call it tail. So initially, if we have one item at the linked list, so tail pointer and head pointer both will point to the first node. As we insert the second item, say I want to insert number 8, what I can do is I keep head pointer pointing to the first element, so I point tail to the next element. So when I insert number 15 or the third element, what I can do is I keep, each time I insert a new item, I keep moving tail. So here tail is moving, pointing here. But when I insert the last element, so what I can do is, again, I'm gonna move each time the tail pointer pointing to the last element. So if I insert another item here, say I create a new node and I want to insert it here, so I move the tail pointer while inserting the node, so tail pointer is pointing here. So this way, when we insert at the end, we can make the time the time complexity of this function big O of 1. So I'm not gonna use a loop here. So what I'm gonna do, beside keeping a head pointer, I will keep another pointer. Let's call it private node tail pointer. So initially, when I create the linked list, so tail pointer is going to point to null, and also this dot tail pointer is also going to point to null. So when I create the first element, both the head, I make the head pointer and the tail pointer point to the first element, or the initial element, or the initial node. So let's do that. I make head pointer point to the new node, and also I want to make tail this dot tail pointer pointing to the new node. So here, every time I insert a new node, I'm gonna use the tail pointer to insert the new node to the tail, and once I insert the new node, then I will make the tail pointer point to the new node. So once I insert number 8, instead of having tail pointer pointing to not having number 3, I will move the tail pointer to point to the new node. In that case is number 8. When I insert number 15, I do the same. So let's do that. Using the tail pointer, I can do tail dot next equal to new node. Once I inserted the new node at the tail pointer, so I move the tail pointer to point to the new node. So right now the new node is going to be tail pointer. So tail equal to new node. So this way we can bring down the time complexity of this insert at end to big O of 1 by keeping another pointer, tail pointer. So if we run our program, we get the same result. So this way we can insert an item at the end of the linked list. So in the next videos, we will see how to insert at the beginning and at the middle of the linked list. Thank you guys for watching, and see you in the next video. Bye bye.